Alright, welcome to ComSConnection. This is going to be a walkthrough on Blackboard of mergesort, the mergesort algorithm, and exactly how it behaves and how it would sort these numbers here on the very top. Now, before I get into the actual steps and start walking through the process, I'm first going to explain the benefit and also kind of outline how this will work. So, what we know about mergesort right now is it has 3 steps, or 4 technically. First, it's going to decide if the base case is present. In other words, mergesort's base case is, can we not split this any farther? Is there already basically one element that we're working with? If we cannot split it any farther, then we just go ahead and return back to wherever the mergesort was originally called from. If we can indeed split it into smaller pieces, in other words, if our subarray that we're given is at least 2 elements or larger, we know we can divide it into a left and right side. So we recursively call mergesort on the left side, and then we recursively call mergesort on the right side of the subarray that we were originally given, and then we merge those 2 halves back together. The magic of this is that by the time this statement here executes, by the time we merge this subarray, these two, the divided subarray, back together, we're going to assume that they're already in ascending order on both sides. So as you can see, I've drawn a subarray here with 1, 3, 5, 7, 9, 10, 11. We know that those are in ascending order. The smallest element is the first element. And we have a right side that also follows that same pattern. 2, 4, 6, 8, 10 is also in ascending order. So we know that the smallest element must be the first element. Now, to have something to compare that against, let's look at this array here at the bottom. This is in descending order, starting from 12 and going all the way down to the number 1. Let's ignore this on the bottom for now, and let's assume that my original call to mergesort is on this step, merge. We've already divided up the left side, we've already divided up the right side, and following true with how the mergesort algorithm will actually work, by the time that merge executes, we know that we're going to have 2 ascending order arrays, 2 arrays that are already sorted, 2 subarrays that are already in ascending order. So all we have to do here is we know that since this is the smallest element in the left subarray and this is the smallest element in the right subarray, we automatically know that we only have to compare this element here with this element here. Whichever one is smaller automatically becomes the element that is our smallest in our entire array. So the checking is much easier with mergesort, and this is the real advantage of doing it. We know automatically that 1 is less than 2, so we can put 1 right there. Then we don't ever need to check that cell ever again. Now all we need to know is whether 3 is larger, or which one of these is smaller, 3 and 2. So basically we have counters here that start at 0, and we just say, I want to check the ith element of the left subarray against the jth element of the right subarray, determine which one is smaller, the actual values, copy that element into our new array, and then we're going to increment this counter. So since I is now 1, we know that we can compare the 0th element of the right subarray against the ith element of the left subarray, and we can put 2 right here, cross out 2, increment this to 1. We don't really cross it out, but by incrementing you accomplish that task. Now 3 and 4, we put 3 here, make this 2. 5 and 4, we put 4 there, make this 2. Then 5 and 6, we're going to put 5 in there, so we'll make this 3. Then we have 7 and 6, so we'll put 6 there, make this 3. Then we have 7 and 8, obviously we put 7 there, make this 4, so this is getting pretty tedious, you see how this is going to work. And then set 8 and 9, we're going to put 8 here, cross this off, but now, all of a sudden, we've run out of elements on the right subarray. There's no more elements to compare these elements to, so we automatically know that we can just copy the remaining elements of the other subarray, the one that still has available elements, into our new subarray in the order they're already in, and we're guaranteed to have a sorted pattern. So did I skip 1? Oh, I did skip 7. I skipped writing 7 in there. So we'd have 7, then 8, then 9, then 10, and then 11, one at a time, just copying those in. So that's how the merge step actually works. And now I'm going to step through the recursive pattern, and we'll see how we get everything into ascending order before that merge step ever increases, or ever executes, I should say. To compare that against something like bubble sort, which is a much less efficient algorithm, we're going to look at this bottom array here. If this would be our worst case scenario, if they're in the exact opposite order we want them in, say we want all of these elements in increasing order in the same sense, well, the first step is we find the largest element and place it at the end. So one at a time we'd say, well, 12 is bigger than 11, so we're going to put 11 here and 12 here. And then 12 is bigger than 10, so we're going to put 10 here and 12 here. And then 12 is bigger than 9, so we're going to put 12 here and 9 here, and so forth and so on. So by the end, you end up with 12 here, and then 1, 2, 3, 4, 5, 6, 7, all the way up to 11 here. And then you still have the largest element on the left. So this would be worst case scenario. Obviously that's not going to happen every single time, but you're guaranteed with something like merge sort where that's never going to happen because you're always going to have the two smallest elements at the front. Whereas something like this could potentially cause you to have to check every single number against every single number as many times as there are numbers. So we call that a big O of n squared algorithm, meaning that it has to do, if there's n number of elements, in this case 11, or 12 I guess, 12, then we would have to check it 144 times or do 144 steps at worst case before we're going to complete this algorithm. So that's just a little bit of comparison there. And now let's step through our actual merge sort algorithm. So we'll work with this. I'm going to erase some of this. I'm going to erase this left and right so we don't run out of space. So the first thing our algorithm is going to do is determine our midpoint. So since we know we're not at the base case, we're going to determine a midpoint. This is a size 11 array, meaning that this is index 0 and this is index 10. So we take the right side minus the left side and divide that by 2. In this case, we're going to have 5. So let me do this for ease. Yep. All right. So we'll divide here. Then we'll basically call merge sort on this sub array. So we pass it into a new recursive call. So I have my stack. I'm going to erase this completely so I can draw a nice little stack for us. So we have our stack here, main. Main calls our first merge sort. And then that has, the entire bound 0 to 10. Get a new piece of chalk here. This one sucks. All right, and then we're going to get basically another call to merge sort with bounds 0 to 5. Now we basically divided this array into these pieces. Now again, we know we're not at the base case, so we're going to find a midpoint again. So 5 minus 0 is 5, divided by 2 is going to be 2. So now we have this subarray here, 0 to 2. Another call appears on the stack. I'm just going to call it MS for short. 0 up to 2. We can still split that. So we're going to take 2 minus 0 divided by 2 is 1. So we're going to divide here. And then that's size 2. We have basically a 2-element array. So we're going to call merge sort again. So notice that we haven't actually done anything with the right sides yet, because the left sides, each recursive call or each element on the stack is still waiting for the left side to finish before it ever returns and then can execute the right side of the algorithm. So for this case, or just make note of that for now, but for this case we're going to, again, further break this down. And so since we have a 2-element array here, 1 minus 0 divided by 2 is going to be 0. So we're going to end up calling merge sort with the size 0, 0 array, which is basically this one piece right here, which is the element 15. Well, that is our base case. We can't divide this into 2 half elements or anything like that, so we know this is the point at which we need to just return. So we're not going to do anything with that. But now on this level of our stack, which let me go ahead and erase this. When we're back to this level of merge sort, it knows that it's done with its left side. It's been returned. So now it's going to do its right side, which will be 1 and 1. So we'll create another merge sort call on the stack with the bounds 1 and 1, which, just like before, is only a size 1 subarray, so we can't divide it any farther. So we know we're stuck with just one element. So we'll go ahead and return on the base case. Now, this level of merge sort can call merge. So I don't need to step in through all the details of merge again, because you guys saw it illustrated there on a much larger scale, but we know we're going to end up with 4 and 15 here. And then now that left side is done. So you can maybe already see how this is happening, because this level of merge sort here, which was this one just returned here, 0 and 1. So 0 up to 2, it has now completed its left side. And as you see, it sent it in with 15 and 4, and it got it back as 4 and 15. So you can hopefully already start to see how these subarrays become sorted before they get back. Because even though this original call to merge sort has never called merge, which is where the actual sorting occurs, the recursive calls that get called after it have higher priority and have to complete before it ever dominoes back to the original call to merge sort, and therefore we can't possibly have therefore they will already be sorted, because many other calls to merge have already been made before the original call to merge is made from the original call to merge sort. If that doesn't make sense, rewind this video. That's the magic of modern technology. So now we're going to divide the right side, knowing that we only have one element. Our midpoint was defined as 1, so we take 1 plus 1 is 2. Then we're going to call merge sort with the bounds 2 to 2. So, well, that's only one element, so we can't divide it any farther, so we've got 0. Well, now this returned here, and we're back to 0 and 2, and this can call merge sort. 0 is going to end up here, 4 is going to end up here, and 15 is going to end up here, and then we're done with that side. So now this has returned 0 to 2, and we're back to merge sort from 0 to 5. Now that we've completed the left side, let's get our right side. We know that we're working with 3, 4, and 5, so that's again 3 elements. So we're going to take 5 minus 3, which is 2, divided by 2 is 1, or plus the left side. So actually it would be 5 minus 3 is 2, so it would be 3 to 4. 3 to 4, our dividing is right there. We can still split this farther. Hopefully, I don't need to do the stack anymore. Hopefully you guys get the picture here. Each level I'm drawing is another stack. So we know that this is a size 2 subarray, so we're going to divide it again. It's going to end up here. This is going to be the element 13. Obviously that's going to return when it calls merge sort on a size 1 subarray. It's going to say, well, that's from 3 to 3. So that's a size 1, so that gets returned. Returns 13. Then we'll call merge sort on this element here, which is going to be 8. They'll get swapped. 8 will go here, 13 will go here. This has been returned after merge completed. We get our right side. It's going to be 7. Obviously that's a size 1, so it just returns back there. And then this level of the stack here, this merge sort call, executes merge. We get 7, we get 8, and we get 13. Then this one has completed. Now we're back to our 0 to 5 merge sort call, which can now merge these things back together. So 0 is their smallest element, then so that will get crossed off. Then we know 4 is our next smallest element, so that will get crossed off. Then we have 7, then we have 8, then we have 13, and we've ran out of elements in our right side, so we add 15 to the end here, and we've ran out of elements in this side. So merge is completed on this level, and we can delete this off the stack, even though I said I wasn't going to trace through the stack anymore. Now we're back to merge sort up to 0 to 10. We've completed our left side, so let's go ahead and do our right side. Step through this pretty quickly. We have 5 elements here. We know 5 divided by 2 is going to be, so it would just be 2 elements. And then obviously we can divide that into 2 smaller elements. We've got 1 here, that's size 1, it'll just return. We've got 9 here, that's size 1, so it'll just return. Nothing changes. Then we'll do the other side of this, which will be size 3, so it'll divide here. Size 2 array on this side, so 1 will be 12. I said 12 and wrote 13. The first element here is going to be 12, and it divides on this side, so the right side is going to be 18. Those get merged back together on this level of the stack, so we're going to end up with 12 and 18. Now on this level, the right side is, or the left side is done, so we do the right side. The right side is just going to be this one element 3, which will get returned back here once merge is complete, or in base cases, so nothing happens there. These get merged back together, 3, 12, and 18. Now this level of the stack is done. Now we're back to bounds from 6 to 10. We've got the left side on this side here, and the right side on this side. We're going to merge these back together. 1, 3, 9. Then we ran out of elements on the left side of the stack, or the left side of our subarray here. So we'll go ahead and copy the remaining elements from the right side. Those are both done. Delete that off the stack. And now finally we're back to our call to merge sort with the bounds 0 to 10, which will merge these things back together. So 1, 2. All right, so 0 and 1, 0. 4 and 1, 1. 4 and 3, 3. 4 and 9, 4. 7 and 9, 7. That was the worst 7 I think I've ever drawn in my entire life. 7, better. 8 and 9, 8. 13 and 9, 9. 12 and 13, 12. 13 and 18, 13. 15 and 18, 15. And then we're out of elements on our left side, so we'll go ahead and copy the remaining elements from the right side. And now we have returned this array back to main. This is off the stack, and we have a completely sorted array. So that's it for the merge sort Blackboard walkthrough. There is a merge sort demonstration video that will be up as well, showing this process, exactly how it behaves on a computer, and able to give you another look at this algorithm. So hope that you like this video, and let us know if you have any questions. Otherwise, good luck.